infrared spectroscopy, the energy is more than the microwave spectroscopy, that is in microwave region. So in microwave, only rotational energy levels are affected, that is transition take place in only among the rotational levels. But when we come in infrared region, then the energy is increased, and energy is increased in such a way that here vibrational energy levels are affected, that is transition takes place in vibrational among the vibrational energy levels. So this is also a kind of electromagnetic radiation. We can see from this picture that this is the type of electromagnetic radiation. There are two components of this electromagnetic radiation, or any electromagnetic radiation. One component is electric field and other component is of magnetic field. And these two components are perpendicular to each other. From figure it is also clear, and from this figure it is also clear. One wave is moving like this and another wave is just moving perpendicular to the previous one, and this is the second one which is perpendicular to the first one, and both these waves propagate simultaneously in the same direction. When one wave completes one wavelength, the another component also completes one wavelength. Here lambda is the wavelength which has been shown here. So now we see that if this is our electromagnetic radiations, radio wave, infrared, visible, this one, then ultraviolet, X-ray, gamma ray, cosmic ray, and we know that when we move left to right, that is from radio wave to the gamma rays, energy is increases, but wavelength decreases. From this figure, here it is also clear. Here waves are longer. As soon as we move towards the gamma rays, the wavelength is smaller than the waves of the right hand side. So today our discussion is in the region infrared. So this infrared lies here, it is very clear from the previous one. Here infrared lies between this visible region and this microwave region, and the visible region is so called because in this region human eye can see the object. We know that there are 7 components in visible region, that is from violet to the red, violet, indigo in the form of azure, violet, indigo, blue, green, yellow, orange and red. So the red part of the visible ray is from left hand side, right hand side, and the violet part of the visible region is in the ultraviolet side, and hence they are named also infrared and ultraviolet. Now in this infrared there are 3 regions which is very clear in this figure. One is called far infrared, another is the mid infrared, and then it is near infrared. Near infrared because it is near to the visible, and far infrared because it is far from the visible region. Infrared region, just I have told that the energy is such that it can make a transition in the vibrational energy levels. That is, vibrations are set up. Suppose this is a diatomic molecule and this is exposed to infrared region, then what happens? A vibration is set up in this molecule, that is this molecule vibrates in such a way. This is the normal position, this is the stressed position, and this is compressed position. So due to this phenomenon, a vibration is set up, and this vibration energy is obtained from the infrared region. Now, so this is also called as vibration. This infrared spectroscopy is also called as vibrational spectroscopy. But we know that its energy is more than the energy of microwave. And in microwave, only rotational energies are affected, and hence in this reason it is called as rotational spectroscopy. So what happens? The energy of infrared is more than the microwave, and in the microwave rotational energy levels are affected, that is transition takes place among the rotational energy levels, and in infrared since the energy is more than microwave, that is rotational energy levels, to excite rotational energy levels. So in this infrared vibrational energy levels are affected, which is also affected with the rotational transitions, that is rotational energy levels. That is, in case of infrared, rotational energies are affected, rotational energies and rotational, that is transition among rotational energy level takes place, as well as transition among the vibrational energy levels. So more correctly, here we can write that it is vibrational rotational spectroscopy. Vibrational rotational spectroscopy. If we separate the vibrational energy from the rotation, then it will be called as the pure vibrational spectra. But if it is associated with the rotational energy, then the spectrum will be called as vibrational rotational spectrum. So the complexity in this region, that is infrared region, is more than the complexity of the spectrum in microwave region, because in microwave region only rotational energy is affected and transition takes place only in the rotational energy level. But here rotational as well as vibrational energy levels are affected and transition takes place among both the energy levels. Therefore the spectrum is more complex than the microwave region or rotational spectrum. Now, what is the range? This is very important. Here we see that this starts from 50 per centimeter. This is the wavelength, or here since frequency is denoted by nu, and E is the energy, but it is more common that these spectra are actually expressed in the terms of nu bar, that is wave number, and it is 1 by lambda, and the unit is per centimeter. Unit is per centimeter. So here the unit is per centimeter. This blue unit is this one. If we represent in micrometer, then it will be from the black digits, but blue digits are in the wave number nu bar. So this has three regions. Infrared has three regions: far infrared, mid infrared, and near infrared. Near infrared, it is called because it is near to the visible, and this region is called far infrared because it is far from the visible region. Wave number starts from 50 per centimeter to 50 per centimeter to 1200 per centimeter in this, and from 1200 per centimeter to 4000 per centimeter, and from 4000 per centimeter to 12,000 or around 13,000 per centimeter. This is the range. Mid range, here in the far infrared region, it is three region: 50 per centimeter to 667, and 667 to 1200, 1000 per centimeter to 13,000. This is the near, this is the far in, and the distribution is like this. This region is very important, and it is called as the fingerprint region. Most of the frequencies of different groups and bonds lie in this region, and this is very helpful. This region is very helpful in determining the structure of a molecule. So what happens here, we have seen this electromagnetic radiation has two components, electric component and the magnetic component. So the definition of spectroscopy is also, we know that the spectroscopy is a interaction of matter with electromagnetic radiation. So when suitable electromagnetic radiation interacts with a certain matter, then the electric field of this electromagnetic radiation interacts with the molecule, which has also its own electric field due to presence of dipole moment. So very basic condition which is required obtaining a infrared spectroscopy, that the molecule must have dipole moment and there should be a change in dipole moment. There should be a dipole moment. First condition is presence of dipole moment, and second is there must be a change in dipole moment, which is represented by. If there is dipole moment and it is not changing during the vibration, then we do not get the IR spectrum, which is very clear. We take the example of carbon dioxide. The dipole moment of carbon dioxide is 0, though it has such atoms like oxygen and carbon where there is a difference in electronegativity, but since the two bonds, that is CO bond on right hand side and CO bond on the left hand side, they balance each other, and as a result the dipole moment becomes 0. When it vibrates, because if we expose this molecule, if you expose infrared on this molecule, then whether we get infrared spectrum or not. So there are three types of vibration in carbon dioxide molecule. One is symmetric, another is asymmetric, and third one is bending. In symmetric stretching, in symmetric vibration, the both CO bonds stretch and compress equally from both sides. Both these bonds, that is both the CO bonds on the left hand side and right hand side, stretch and compress equally. So what happens? Polarity is not induced, and if polarity is not induced, then dipole moment will be 0. So in symmetric case, in symmetric vibration, dipole moment is 0, mu is equal to 0. But in asymmetric vibration, both the CO bonds are not vibrating with same fashion. If one bond is stretching to a particular length, then the another bond is stretching not to that extent. It is either less than the previous one or more than the previous one. For example, here we can this bond on the right hand side stretches to such extent, then left hand side stretches to this smaller extent. So in this case what happens? A polarity is induced, and when a polarity is induced, no longer remains 0. It will have certain value, that is here mu is not equal to 0. So our condition is that there should be a dipole moment, and that dipole moment must change. There must be a change in dipole moment during vibration. So here, if this type of vibration is taking place, then definitely there is a change in dipole moment, because in the normal case it has dipole moment is equal to 0. Now the third type of vibration is bending. So this bending is of two types. Bending on the plane of this smart board, or it is out of the plane of this smart board. Suppose bending vibration is taking place in the plane of this smart board, then we can, in the same plane, suppose this angle is x and this angle is y, and if x is equal to y, then this type of bending vibration is taking place. And now what will happen? The value of mu, whether it will be 0 or it will not be 0, certainly it will not have a 0 value. It will have a certain value because dipole moment is a vector quantity, and vector quantity has magnitude as well as direction. And we know that if the magnitude changes, then we say that dipole moment is changing or vector is changing, or if its magnitude remains constant and its direction is changing, then again we say that it has changes in the value of that vector quantity. So mu is a vector quantity, dipole moment is a vector quantity, and here bending is taking place in the same plane with the same angle, that is magnitude is same but the direction is different. Here it is in the right side, it is in the downward side, here is the upward side. So there will be change in dipole moment, and our condition is that there must be a change in dipole moment during vibration. So there are three types of vibration: symmetric vibration, asymmetric vibration, and bending vibrations. So among these three, we see, it is very clear that the dipole moment is not changing during the symmetric vibration, but dipole moment is changing during asymmetric vibration. Also dipole moment is changing during bending vibration. So what will happen? In these two cases, we will get the line in the spectrum for asymmetric vibration and for bending vibration, but for symmetric vibration, we do not get the line in the spectrum. So this is the condition for a molecule which can respond a IR spectrum. This is the another figure from which we can also see that what is the range of different regions: far infrared, mid infrared, and near infrared. Now here the range, which is 700 nanometer to 1 millimeter, the vibration of atoms and molecules take place, and for this region 1 nanometer to 400 nanometer inner shell electrons. This is represented in terms of nanometers, and here these are in terms of per centimeter. So we have presented in terms of per centimeter, and that is wave number terms, or in nanometer terms. This figure is for ultraviolet region. This infrared is between visible and microwave region, and after this visible region, the region is called ultraviolet. UV region. This range, this is also has three regions: UVA, UVB, and UVC. So when we discuss UV, then we will discuss these regions in detail. Now, just for knowledge, now here in this slide, this is very important line, that the wavelength of infrared region is in the 2.5 to 25 micron region compared to the visible light, 400 to 700 nanometer. In case of nanometer, it is the range 400 to 700 nanometer, and in case of micrometer region, it is 2.5 to 25. The frequencies of IR radiation are more conveniently expressed in terms of wave number, which I have explained earlier. Now this is the another figure. We can see that the wave number can be expressed in per centimeter, also in the nanometer. So in case of micrometer, it is from this region. Now before going to details, we have to understand in very short that how this spectrum is obtained in case of infrared region. So from figure, in short, I can say that there is an IR source, tungsten bulb, and this portion is the monochromatic system. That is, when IR radiations passes into monochromatic region, then a monochromatic light is obtained. And in the monochromatic system, there are cuvettes in the instrument. There are two cuvettes, one for sample, another is for reference. So it is called a double beam spectroscope, double beam. There are two beams splitting there. From one passes through sample, another passes through the reference. And when this passes through the splitter, then it splits this monochromatic wave, and then passes through detector, and then from readout, that is the system where we take printout, and for reference, further reference, we keep in the record. Now, one thing I shall discuss in addition to this, that in infrared spectrum, there are two types of spectrum. One is called as emission, another is called as absorption. Another type of spectrum is called continuous spectrum. This is very clear that if we pass white light through a prism, then we get 7 colors of light. But these 7 colors of light are not separated with each other with a separate boundary, with a definite boundary. But some regions or some colors are overlapping on each other. And finally what happens, that a continuous spectrum is obtained. This is also called as band spectrum. This is rainbow is the example of band spectrum. Now, emission spectrum. So, what happens when we want to take emission spectrum? Then the substance is to be heated, and it is converted in the form of in the gaseous form, and in the gaseous form, its particles by absorbing energy goes to high energy level, but for a very long time it cannot stay at the level. It comes to the lower energy level, and when it comes to the lower energy level, it emits the absorbed energy, and when energy is released, that energy which is emitted, that is captured by the machine, and it gives result in the form of some lines. There are discrete lines here, and this is the form of emission spectrum. But there is another type of spectrum also, which is called as absorption spectrum. So in absorption spectrum, what happens? A source is used, and when this source of light passes through a certain material for which we have to take the spectrum of that material, then a certain amount of portion or wavelength or energy is absorbed by the material and rest is emitted. So rest is emitted, and this type of spectrum is found in which wavelength or the energies which are absorbed by the material are missing in the spectrum. So what happens if we take the absorption and emission spectrum? If we combine these two spectrum for the same material, then we get all the wavelengths and the energies in the spectrum. So here line is obtained, but for the same substance, here line is missing, because these energies or these wavelengths are absorbed by the material, but here it is emitted, and here it has been these portion, these energies or these wavelengths are absorbed by the material. This source has all the wavelengths, but in the spectrum some wavelengths are missing. These are the wavelengths which are missing because these wavelengths have been absorbed by this material. So these two types of spectrum, according to our requirement, we get for a substance. One is the emission, where the emitted light is used for making the spectrum, and another is for spectrum. Another is called absorption spectrum, in which some of the wavelengths are absorbed by the substance, and the remaining portions, for remaining portion, we get the spectrum in which those wavelengths are missing. From the example, it is very clear. That is, if this spectrum is for the same substance, then these are the lines which appear in the spectrum, and these dark lines are the places or the wavelengths which are missing in the spectrum. Here it is missing. This is another slide from where we can see the wave number, frequency and energy which are converted into each other and has been shown in the same place simultaneously. For reference, if you want to express in the form of energy, if you want to express in the form of frequency, if you want to express in the form of wave number, then from this table we can write one or the other. So for today, the last slide, and this is a very vast topic, and this is part 1, my topic infrared spectroscopy. From the second part, we will start derivation of the expressions, how energies are derived for the infrared spectrum, and what inferences we can draw from those energies, and also we will discuss the selection rules. And thank you.